Right, welcome to London Learning Lean. Next week we've got Kenny Lau talking about perfectoid stuff, but this week we're very pleased to have Amelia Livingston, LSG&T student, who's going to tell us about group cohomology in Lean.
Thank you very much. Okay. So since this summer, I've been working on something in Lean that quite a lot of people in the past have worked on before. So for instance, Shen Yongwu and Anka Kibanu and Kevin himself, but it's always as like master's projects and things. So it's never made it into MathLib, and you know, it's low-hanging fruit. Like it's pretty basic maths, and there aren't any large barriers to formalization, but it's not there yet. So I've been trying to get it there, and I think one thing that's made it easier for me this time around is that in the past year or so, there's been a lot of homological algebra progress in MathLib. And that's because there's been this massive project going on called the liquid tensor experiment, where a bunch of Lean experts formalize some results of Schulze. And yeah, due to the people working on it and the thought that's gone into it, I think people are finally realizing how to correctly do homological algebra in Lean, and yeah, because it's a really good stress test for any ideas that you come up with of how to implement this stuff. And so I think I've benefited from that a lot, and so I'll allude to it quite often because yeah, it's been a big factor in my work. So first of all, what is group cohomology? Well, we're used to studying group actions on sets, so to learn about a group from its actions on sets. And one thing we can do is to assume that those sets are also additive groups, such that the action of the group distributes over the addition in the additive group. And in a sense, this generalizes representation theory, because if you have a homomorphism from a group to the endomorphism group of a vector space, then that makes the vector space into a G module. So before we go into how we calculate it, a bit of motivation. One nice, very low-level application of group cohomology is that it can go some way to allowing us to classify extensions of groups. So what that means is if you've got an abelian group A and another group G, we can ask what groups E exist where A is a normal subgroup of E and the quotient E mod A is isomorphic to G. And so, yeah, first of all, like you can imagine that if you've got homomorphism from G to the automorphism group of A, that always gives us a semi-direct product structure on A cross G. But that's the sort of least interesting group structure you can get from given a G action on A. And it turns out that like, yeah, E in the middle is always set theoretically going to be A cross G, but the interesting structure is determined by the multiplication law, and it turns out that the second group cohomology group corresponds to equivalence classes of group extensions up to some notion of equivalence. So, and yeah, when A is not abelian, you can like go some way to doing the same thing by taking cohomology, but you're taking the center of A instead of all of A. As you might imagine, group cohomology has relation to other cohomology theories. So if you've got a group and you take the singular cohomology of its classifying space, then that's isomorphic to the original group cohomology. It's got applications to algebraic K-theory, which I don't really know about. And then one nice application is that if G is a topological group, then we can require the action of G on a G module to be continuous, where we give M the discrete topology. And so an important example of this is when G is a Galois group, which we give the profinite topology. And when we analyze that, we get Galois cohomology, which is really important in number theory. So some examples, like the first cohomology group of the action of Galois group of a field extension on the unit group of the bigger field is trivial, and that's Hilbert's theorem 90. But the second group doesn't have to be trivial, and that's the Brouwer group when it's the Galois group of the separable closure. So yeah, that's a direction I'd be interested in applying this work to. So what actually is group cohomology? Well, we've got a functor from the category of G modules to the category of abelian groups that sends a G module M to its group of G invariants. And this functor is left exact, it's additive, so it has right derived functors. So yeah, you can imagine we can get some cohomology from that. But we don't want to, because right derived functors suck. Like injective object, you'd have to take an injective resolution, and injective objects are really big and unwieldy. So really we want another way. Here's one way. We can define things called inhomogeneous cochains, which that doesn't look very good. You take a complex from the set of functions from powers of G to M, and you can take the cohomology of this, and this gives you group cohomology. And the differential is a bit of a mouthful, but you know, it's a lot nicer than trying to find an injective resolution. So that's one way. And yeah, they show up in nature. So using this complex makes it really transparent that group cohomology corresponds to group extensions, because if you look at the first differential, then it has that equation, and you compare it to in the group extension problem, you have these set theoretic sections that give you a group structure on the middle on E, and yeah, they have to satisfy this relation that looks a bit like saying they're a homomorphism, but not quite. But the fact that they satisfy that, as you can see here, makes them a one cocycle in the cohomology sense. So yeah, and we should check that the zeroth cohomology is actually what it's supposed to be, but that's quite clear because the first differential, whoops, you're looking for the kernel of this map, and yeah, it's just elements of M that are fixed by all of G. And the higher cohomology groups match up too. Another feasible way to calculate group cohomology is with the homogeneous cochains. So I mentioned this because when Kevin had worked on this, he'd already defined homogeneous cochains, so I just used them. There was like no deeper reason for that, but yeah, the homogeneous cochains are the functions again, but this time they have to satisfy some notion of G linearity, and we get a much nicer differential that's, you know, quite a familiar expression. And this time, yeah, you have to check that this really is group cohomology again, but that follows from the fact that the kernel of the first map is the constant maps, and by G linearity, f of 1 has to be G invariant, and you get a bijection with the G invariant subgroup. So why do we get these nice concrete cochains for free? Where do they come from? Well, as you might know, it's because we're actually calculating X groups. So there's an isomorphism between group cohomology and the X groups over the group ring of your group. So G module really is a good name because actually we're doing homological algebra over rings and modules. So there's multiple reasons for this isomorphism, and you know, I'm trying to build this correspondence in Lean, so we have to choose a reason to formalize. And the abstract reason, the deep reason, is that derived functors are universal delta functors. So what that means is, well, cohomological covariant delta functor is a family of functors indexed by the naturals, and from any short exact sequence, we get things that are like connecting homomorphisms, and they induce long exact sequence, and there's some commutativity property. So it's kind of, you know, it's immediate that derived functors are delta functors. They just look like derived functors. But a universal delta functor is defined through, so a morphism of delta functors is a family of natural transformations that make the appropriate diagram commute. And then a universal delta functor is one that's determined by degree 0. So it's one that all the maps, if S is a universal delta functor, then any map out of S is determined by the natural transformation from S0 to T0. And it's a theorem that derived functors are universal. So they're determined by degree 0. And this is because they're effaceable, which is French for erasable, and erasable is like quite a good name. So an erasable functor is an additive functor of abelian categories, such that for all objects A and C, there's an M and a monomorphism from A to M that the functor sends to 0. So if you've got a right derived functor, then all the higher derived functors are erasable because you can just take M to be injective. And there's a dual notion of this for like epimorphisms that left derived functors satisfy. So then the theorem we have to prove is that erasable delta functors are universal for all the higher, for a degree greater than 0. So here's some of the proof. I won't go through it all, but yeah, we have to take an object A and find a monomorphism that erases it, and then suppose G is another delta functor and that we've got a morphism out of it in degree 0. Then we want to find, we've got this F0, we want to find F1, and then all the higher cases are quite similar. And yeah, so the top row is right exact because of our erasability assumption, and the kernel of the of delta F on the top here is contained in the kernel of delta G composed with F0. And you can prove that because the left square commutes. So the kernel is the image up here, and then when it gets mapped down by F0, you're in the image of the bottom left map here. And that means you can uniquely define an F1 down here by the fact that, it's well defined. And then we have to prove that this F1 is first of all functorial, and second of all commutes with the delta maps. So I won't prove it, but showing that F1 of A is functorial follows from checking that the side of the back here on the right commutes in this massive cube, because we know all of the other sides commute. And then to show that it commutes with delta, again, we have to check that this back side, this right-hand side of this prism commutes, and we know all of the other sides commute. So it's like, I don't know, there's a lot of objects and maps to be dealing with, and you can imagine that if you're formalizing this, at the very least it's going to look a bit crazy, but it's possible. So the deep reason that group cohomology is X'd is because they're both derived functors, so all we need to do is check that they agree in degree 0, and we know that because if you take a hom in the middle here from the trivial, we're taking the trivial G module, we're taking the integers where the action of G is defined to be trivial. And so if you had a hom out of this, it would be defined by where you send 1, but you're going to have to send 1 to something that's G invariant because Z is G invariant, and so you get this isomorphism. So we could show that and we'd be done, and it would be like nice and deep and general, but we wouldn't have any of our nice cochains, and like everything you do in group cohomology uses those cochains somehow. Like we'd be missing a large part of the theory that you use to apply it to anything.
Not everything, I guess. But yeah, lots of things. I mean, the spectral sequence doesn't use them, right?
Yeah, but
lots of applications use them. We need both, right? That's the problem.
Yeah, and there's stuff in low degree, like there's stuff like group extensions and stuff. You want the concrete cochains for many things. Another reason not to do it this way is that in MathLib, X is not a bifunctor yet. It's just because when you learn about X being a right derived functor, you very quickly afterwards learn that it's also, you can calculate it by resolving the first argument too, by using a projective resolution. And so the definition of X in MathLib is is we don't even have injective resolutions yet. Like, it wouldn't be hard, but we only have projective resolutions, so X is defined in terms of projective resolutions. So it's much more accessible to just ignore the universal delta functors for now. But it's worth having a look at how close we are to doing it this more general abstract way. So here's some stuff from the liquid tensor experiment repo, because none of this is in MATLib, but it's nice to have a look at what people have defined and how they've defined it. So they've got delta functors. Everything's very functorial. You've got this functor from a short exact sequence to the third object in the short exact sequence, stuff like that. I think they also have universal delta functors in some branch somewhere, but as far as I know, there's not much more than the definitions. They've got the connecting homomorphism in the long exact sequence of X. So MATLib doesn't have long exact sequences, but you can, it's not that hard to define the connecting homomorphism. It's just something that makes all of this hard is like, if you think about, that's the next slide. If you think about the snake lemma or the 5 lemma, you've got these big grids of objects and big collections of maps and big collections of assumptions. And so this stuff doesn't look like anything you see in MATLib because there's like loads of things. Like, I have no idea how far away this is from being PR'd, because it's inherently different to anything else in MATLib. But you can assume that it's done pretty well because of the time and thought and stress testing and the lean expertise of the people working on it. So you've got stuff like a functor out of the set of 4 elements and stuff. I think making everything functorial is a good way to do this that you don't immediately think of when you just try and roll your own, basically. This is API for creating functors out of little sets. They're using lists to do exact sequences, so that's not something that's anywhere in MATLib, and it's quite intuitive. Like, if you were going to decide to formalize sort of finite exact sequences, you might think, I will use a list, and it's nice to see that the intuitive approach works and is getting used. So it would be nice to see that in MATLib. The less deep, more concrete reason that group cohomology is X'd is that we can calculate it from a projective resolution instead. And we're going to have to, instead of just checking degree 0, we're going to have to actually define the projective resolution and define a homotopy equivalence, but with something else. But it's much more accessible, and that's what I've done in Lean. So I've taken one of the cochain complexes that we defined earlier and shown that it's not just homotopy equivalent, it's isomorphic to taking homs of a certain projective resolution of the trivial ZG module set. So here's the projective resolution that we'll use. It's the group rings of different powers of G. And again, we've got this nice simple differential of just taking an alternating sum. Just to comment on the differential, because it's like the kind of expression you see everywhere. You see it in like algebraic topology, and there's a reason for that. Here's my proof that the differential squares to 0. It's like long and just only applies to this situation. And then here's, in theory, maybe another proof, which just landed in MATLib before Christmas, about simplicial objects. Now, I don't really know much about this, but I think a simplicial object is a contravariant functor from the simplex category to another category. And the simplex category has like objects and natural numbers. Like, it's quite weird. And the morphisms are certain tuples of natural numbers. And the way to prove this expression abstractly is to do it in terms of simplicial objects. and there's this thing called the Dold-Can correspondence that lets you move between these and chain complexes. So yeah, really you're taking a differential and alternating face map complex. I have no idea how much work it would be to apply that correspondence and use this proof for my situation, but I thought it was kind of cute. So, oh, whoops. Okay, so when we build our projective resolution, the first thing we need is the objects, and they're already in MATLAB in that we've got the monoid algebra, which is taking a semi-ring K and a random type G. Actually, it's functions that are functions from G that are 0 all but finitely many elements of G. And I was trying to use this for a while, and to talk about a lean specific thing for a bit. Yeah, I think I kept getting instance clashes. So that means that I would have different definitions of scalar multiplication, and lean, when lean tries to read the notation that you're telling it, sometimes it has to look through a list of things called instances and work out which one you mean. And it's easy to create diamonds, which is when lean synthesizes two different instances, but they're not definitionally equal. And so you have to be careful of this. You have to sometimes not define your own instances and make sure it change them to defs, which means that lean can't see them during its search. And so, you know, I kept getting weird diamonds. So this was back in the summer, so I can't precisely state the problem, but I think I changed all my instances to defs so that I wasn't interfering with lean search in any way, but the problem persisted. And in the end, what fixed it was just making this definition group ring, which is literally monoid algebra, but all of the instance clashes went away. So it's a kind of funny thing where, like in real life, we often have different words for things depending on the context that we're using them in, that are just synonyms, and you also have that in lean. And I'm PRing stuff about group rings at the moment, and one of the questions that comes up is that a tenet of MATLAB is to always do everything in the maximal generality. So it helps with organization. And so you can, the definition of monoid algebra is very general. And in theory, you could take Z to be any commutative ring. And you could either define a group ring over Z and then tensor with arbitrary commutative rings, or you could at the beginning define a group ring to be over an arbitrary commutative ring. And it's quite hard to see what's the best choice to make ahead of time. I'm scared because when I was doing this, I had so many weird instant clashes. I'm kind of scared of creating more diamonds. But yeah, that's a question to be resolved at the moment. Yeah, some of the API for group rings is, I basically was constantly proving that things are ZG linear, like that's the majority of the code in all my files. So when I factored out these lemmas, everything got a bit shorter. Yeah, useful advice for life, always factor out lemmas as soon as possible, like use the brain power and the effort to don't have any long proofs. I still haven't learned that. Okay, then we need to check that these group rings are projective, and instead we will check that they're free. So in lean, to define a free module, you take an R linear isomorphism with some free module generated by a set. So yeah, there's my map to a basis. So this is different from what you typically see in like group cohomology notes, because I think in real life you often have a bit more flexibility when you're showing something that's free. I don't know. I really I kept when I was doing this at first, I kept trying to define maps that weren't ZG linear. So what you need to do is take the set G to the n plus 1 and mod out by the action of G, and then you can actually define a ZG linear map that just sends a tuple to the equivalence class of that tuple mod, in orbit. But you have to take out the 0th element to make everything well defined, and that works. There's the inverse, and and you have to check the inverse is well defined because you're just taking an element of the equivalence class, but it is. So yeah, so you've got that your group rings are free. So next you have to put them in a complex, and this is where it gets unintuitive, because in real life, if you have a cochain complex C indexed by the integers, you've got a bunch of objects C to the n, a bunch of maps C to the n to C to the n plus 1, right? That's that's the definition, plus an assumption. And it's easy to ask whether something like an element of C to the n is in the image of D. So say you've got y in C to the n minus 1 that should map to x under the differential. In Lean, it's not so simple, because actually, if you look at this collection of maps, they're defined to be from C to the n to C to the n plus 1. So when we apply 1 to y, we're going to end up not in C to the n, but in C to the n minus 1 plus 1. And it's true that n minus 1 plus 1 equals n, but we're not proving a theorem. We're trying to supply data. We're trying to supply an element of C to the n. And the way dependent type theory works, every term is a term of a unique type. So we can't just rewrite one type with another type. We can't just, we can't apply the theorem that two types equal, because type equality is quite complicated. You can struggle along for a bit, but your life will just start to increasingly suck. And it's just not the dependent type theory friendly way to think about this. So the people who are working on LTE thought out of the box on this and just changed the definition of a complex. So here's the definition we have now. So you have some arbitrary relation on your indexing type. So in a chain complex, it's that the next number is 1 less than the previous number. And you have maps for every pair of elements of the indexing type. So yeah, you don't just have a map to the next object, you have a map to absolutely every object in the complex. And most of them are 0, obviously. And it still matters that most of them are 0, but when you're defining data, you don't have to feel this issue. You just have to, you're outsourcing the work to a place where it's dependent type theory compatible. So this definition has made everything a lot easier, because I was working with homological algebra in a year ago as well, and it was a very different story. So with this, we can define the differential, and as you can see, it's defined for every pair of natural numbers in this case, but with assumptions that they're the natural numbers that they should be. Something I never noticed when I learned this stuff was that when you define a homotopy with showing that if you have the projective resolution and then you put Z on the end of it, then it's homotopy. It's a null homotopy. The identity is null homotopic. And the standard homotopy that you use to show that is not ZG linear. So you have to go to the category of abelian groups, and if G is finite, you can just take the standard homotopy and sum it over all of the elements of the group, and that is ZG linear. But yeah, we want to be general. And for some reason, having to go to abelian groups made everything really there's this statement that if a complex is exact as a complex of abelian groups, then it was exact to start with. And for some reason, I can't do this. Like it's all stated in terms of the category theory library. And it's just really simple, annoying thing that I've tried in earnest at twice, and I can't do it. I was recently, the other day, I was working with the category theory library a bit more, and I think I've made progress in using it. But so I'll give it another go. But it's sometimes the silly things that you get stuck in. So here's the projective resolution altogether. And yeah, you can't see Z there. You can only see this thing called trivial G. And that is because more like lean specific stuff, we're not using Z, we're using U-lift Z. We have to, there's these things called universes, and they parameterize type hierarchy. So like Z itself is in type 0, and type 0 is in type 1, and type 1 is in type 2. And these indices are universes. And this isn't something that most mathematicians ever need to think about, but you run into like logical problems or something if you try and quantify it over all universes, or sometimes you need one universe to be at least as big as another universe. And in this case, the statement that a projective, that a free module is projective, you need your module to be in a bigger, in at least as high a universe as your ring. So because we're doing things generally, we've got G in the universe U, and our module over it is Z, so it's too small. So we have to lift Z to the universe U, and then prove that a bunch of things, like all the properties of Z, can meet with lifting it to a higher universe. And this is kind of annoying, but it's, you know, I just mention it because like this is something I didn't understand about lean for a long time and was scared, but you can just it's not that scary. Another thing is that the definition of X, you know, when you're learning, you have chain complex, projective resolution, and you turn it into a cochain complex. You don't do that in lean. It's hard. You can't really do that in lean. What X actually does is takes a chain complex in the opposite category and takes the homology of that instead of the cohomology. And obviously, like it's the same, but we didn't have any API for that. So yeah, I've got like a 400-line file about moving between chain and cochain complexes. And as a remark, if you use the Dold-Kann correspondence and you talk about simplicial objects instead of chain complexes, then because they're defined to be a functor, and there's a bunch of basic stuff about like opposites of functors, whatever, then this is immediate. So here's the isomorphism from the n homogeneous cochains and the ZG linear maps from ZG to the n. I have no idea why this is so long. I think I golfed it a bit, but yeah, it's just quite a long isomorphism. And then something that's you have to sometimes define isomorphisms between things that aren't just provably isomorphic, but are definitionally isomorphic, which seems really silly, but it's sometimes a type, you know, the way rewrite works is that it rewrites, you can, if one side of a theorem is syntactically equal to what you want to apply it to, you can use the tactic rewrite. And syntactically equal means it's literally the exact same characters in the statement. And there's this more general definition of called definitional equality, which is where, like, say I had an object X and I made a new definition called Y, and defined Y to be X, then they're not syntactically equal anymore because one of them is X and one of them is Y, but they are definitionally equal. You don't have to prove a theorem to show that they're equal. They're just equal by definition. And I really like definitional equality. I like, what's the word? Like trying to use it whenever possible, like trying to get lean to see it whenever possible. Kevin says that I bully Raffle because I'm always trying to like push definitional equality too far. And actually, sometimes when you're defining an isomorphism and the one side isn't syntactically equal to what you're trying to compose it with, then Lean can't, like, sometimes there's just too much to unfold, and you have to use isomorphisms where the isomorphism is defined by Raffle. So that's silly. Yeah, the complex of homogeneous cochains is isomorphic to taking homs of the projective resolution. So in particular, they're homotopy equivalent and give you the same cohomology. So there's that. So yeah, I'm basically done. I have like a bunch of maps to compose, and then I am done. But it's easy to say you're done in Lean and then come across a massive error. But I swear that in the next hour after I've done this talk, I could go away and actually define an isomorphism from X to the cohomology of that cochain complex. But I can't right now. Yeah, this last file, it's just like you have sort of layers of definitions and you suddenly start getting weird timeouts. So here's a known issue that's solved. It's called the def lemma issue. Sometimes you try and define a function or something, and before you've even tried to fill in the definition, Lean has a tantrum. You give it a name, you say what the type's going to be, and you say sorry because you haven't tried to fill it in yet, and you get a timeout. In this case, the isomorphism is just tautological. So one way of fixing this is change def to lemma, because a lemma is supposed to be a proof of a prop, and all proofs of statements are equivalent in type theory. And I guess, you know, Lean doesn't worry so much about whether the type makes sense in that case. There's another instance of this happening. So a few months ago, I was trying to define evaluation on the algebraic closure of a field, and before I'd even started, Lean got upset. And I found a fix in that solution, in that situation, that wasn't very, like, didn't apply to the situations. But yeah, more and more people working with like algebra and stuff, anything with a big hierarchy, you start to come across this. Here's a really cute solution due to Gabriel Ebner. If you define this like this definition that takes an element of a type, or or a prop, and you take the constant function applied to, I mean, this is like, I don't understand why this works. It's like, it's such a simple function, but if you put this after the colon equals and then do like right sorry, then Lean is fine. I don't know, it's a weird solution. It's cool. Yeah, here's another timeout. So this is different. I think this was the timeout that made me go to Zulip with my previous issues, of this timeout, and actually they're unrelated. So this is a definition that makes sense, filled in the definition, but then when I try and admit what the type was, and that is the type, like I copied and pasted that from what the type is, then Lean gets upset. I don't know the solution to that. I'd be interested in answers. But yeah, so yeah, I'm basically done, but sometimes you get weird timeouts. Okay, so I haven't actually been working on this for that long in some sense, because in the summer there were like external constraints that kind of ruined it, and then I had to drop it until Christmas. But I have until June to work on it like really solidly. So here are some ideas of what to do next. I've got to define the inhomogeneous cochains. I've got to do some actual group cohomology, so like maybe some of the extension problem, maybe the infres sequence, like this will be nice and feasible. Galois cohomology, Hilbert 90 should be like quite doable. There's a way of generalizing when the G module is non-abelian, then instead of taking group cohomology groups, you can take cohomology sets, which have a distinguished point. And so you can still define a complex because you can say that the kernel is the things that map to the distinguished point. And you still get like you get a short long exact sequence. And yeah, that's quite important for many things. I need to make everything more functorial, but that won't take long. It would be nice to port things from the LTE repo. So like that's something that they've advertised. Like they really want people to take the stuff in the for mathlib folder and get it into mathlib. So it would be nice to take non-exact sequences and credit the right people and get that into mathlib, because that's a barrier for a lot of things. Yeah, and balancing of X and group homology. So that's as easy to define as group cohomology, but it's the functor is you take the largest G invariant quotient of your G module, and it turns out that that's just a tensor product. So of course it's going to be right exact this time. And there's this thing called take homology that I think like links group homology and group cohomology. So that would be a nice thing to do. I don't think I can do all of these things, but yeah, some ideas. And that's all I have to say. So thank you very much. And does anybody
Thank you very much. Okay, I've